Now let's talk about the available energy from a finite energy source. Okay, to understand this, let's look at this TS plot. Now what is happening in this TS plot? We are considering a mass of hot gas at temperature T. So let us say that mass of hot gas is mg. Okay, now this mass of hot gas is at temperature T. So this state 1, it is representing the mass of hot gas at point or at temperature T. So this is the state of the hot gas. Okay, and now what we are doing, we are cooling this gas at constant pressure. We are cooling the gas at constant pressure from state 1 to state 3. Okay, this means state 3, the temperature at state 3 is T0, which is the temperature of the surroundings. So the gas is being cooled. So let us say from state 1 to state 3, you start cooling your gas. So in this process, let us say the amount of heat that is rejected is Q1. Okay, so let me put it here. So this is Q1. Now the same amount of heat, that is Q1, is being used to heat up reversibly a working fluid of mass MWF. So now you have a working fluid of mass MWF. Okay, and we have to heat it reversibly. And for heating it, we are using the same amount of heat that is being rejected while cooling the hot gas from temperature T to T0. Okay, so from 3 to 1 we go up like this, and the mass of working fluid is MWF. Now if you look at this diagram, the heating and the cooling process, they are happening along the same path, and because they happen along the same path, the temperature difference between the gas and the working fluid at any instant is 0. So if you talk about let us say this instant, at this point the temperature of gas is also same and the temperature of working fluid is also same. So due to this same path, the temperature of gas minus the temperature of working fluid is 0, and due to this, because temperature difference is 0, the entropy increase of the universe is also 0. There is no increase in the entropy of the universe. Okay, now let us say the working fluid has been heated from T0 to T, that is, it has gone from state 3 to state 1. Now what happens is, at state 1, because the working fluid has now become hot, we are expanding it reversibly and adiabatically in an engine, or let us say in a turbine, from state 1 to state 2. So this is reversible adiabatic expansion. Alright, so this is what happens for the working fluid. So this is the fluid that we are expanding. Okay, and in doing so, let us say it does some work, because when you expand some hot working fluid in a turbine, you get some shaft work. So let us say that work that we get is WE. So this is the amount of work that we get. So WE, let me write it down. WE is the work output, okay, during reversible and adiabatic expansion of working fluid from state 1 to state 2. Okay, so this is what it is. And after state 2, it rejects heat reversibly and isothermally to return to the initial state 3. So now from state 2, it will go to state 3 and at the same temperature, which is T0, and in doing so it will reject some heat, and let us say that heat rejection, or the amount of heat rejected, is Q2. So let us say this is the heat rejected in going from state 2 to state 3. Now you have a cycle 1 to 3. So 1, 2, 3. It represents a cycle which is working between two temperature limits T and T naught. Right. Now if you talk about this expansion work, okay, now because your expansion or your cycle is happening between T and T naught, so this is the largest possible temperature difference. So whatever this work that you get, it would be the maximum amount of work output. So I can say that this is the available energy as well. Alright, so let's now look at some mathematical relations. Now if you talk about the value Q1, okay, now Q1 is the amount of heat that is rejected during the cooling of the hot gas. So that would be equal to the mass of hot gas, and because the cooling is done isobarically, so you'll have constant so the specific heat at constant pressure of the gas into, now it goes from T to T naught. So this is the amount of heat that is being rejected. The same amount of heat is being taken up by the working fluid. So this is equal to MWF into the specific heat capacity of WF, and the temperature difference is T minus T naught. So this is the value for Q1. Now this is equal to area 14531. 14531, because the area below the TS plot gives you the amount of heat, okay, interaction of the process. So if you look at this whole area, this is the value for Q1. Alright, now going by this mathematical expression, you can cancel off T minus T naught, and you would get mg into CPG is equal to MWF into CPWF. So this is a very important mathematical relation. Okay, now because gas is being cooled, so let's find out the entropy change for the gas first of all. Delta S gas, okay, and this would be temperature from I can say you're going from T to T naught, okay, and you'll be having mg CPG into dt upon T, okay, and this would be equal to mg CPG into natural log T naught upon T. Now because T naught is less than T, and also because gas is losing heat, so this would be a negative value. So the entropy of the gas will reduce. Okay, now let's find out the entropy change in the working fluid. So this is delta S working fluid, and this would be from T naught to T, because you're heating it, and you'll have MWF CPWF into dt upon T. This is equal to MWF into CPWF into log T upon T naught. And for this same reason, and because the working fluid is gaining heat, the entropy would increase in this case. Okay, now we also know that because the temperature at any instant is same for the working fluid and the gas, the entropy rise of the universe is taken to be 0. There is no temperature difference. So I can say that gas and working fluid, it makes up the universe. So delta S universe, which is equal to delta S gas plus delta S working fluid, this is equal to 0. So you can put this under a nice looking red box. Now if you talk about Q2, the Q2 is the amount of heat that is being rejected in going from state 2 to state 3. If you go back to the figure again, so this is Q2 in going back from state 2 to state 3. Okay, this is Q2. Alright, so if you look at this, so Q2 is equal to T naught into delta S WF. Okay, and this is equal to T naught MWF CPWF into log T upon T naught. So this is the value of Q2. Now if you talk about the available energy, and we know this is the difference between Q1 and Q2, which is the maximum expansion work output, isn't it? So we know that Q1 is equal to mg CPG into log of T naught by T minus MWF CPWF into log of T upon T naught is equal to WE max. Okay, so this is what you get. Now this area, that is WE max, okay, this area is area 1, 2, 3, 1. Okay, so this area is area 1, 2, 3, 1. 1, 2, 3, 1. So this is the area which gives you the maximum amount of work output. So this is equal to area 1, 2, 3, 1. Alright, now therefore the available energy, and available energy is also known as exergy. Okay, so let me write down an alternative name for it. This is also known as exergy. Okay, EXERGY. Now therefore the available energy or the exergy of a gas of mass mg at temperature T is given by this value. So I can say available energy Q1 minus Q2, and you can replace the values of Q1 and Q2 over here to get the value for available energy. So you can straight away remember this formula as well. Okay, now if you go back to the an equation that we saw, that is this equation, mg CPG is equal to MWF CPWF. Alright, so if you come back, Q2 is, there has to be a T naught over here. Okay, you can replace this part by mg CPG, so it gives a more uniform characteristic to this equation to remember. So available energy, you can take out mg into CPG common, so you will have mp into CPG common, because this you can replace by mg into CPG, into you will have log of T naught by T, okay, minus T naught of log T by T naught. So this would be the value of available energy. Now this finishes this topic on the available energy from a finite energy source. Now let's move on to the next topic and talk about the quality of energy. So we'll be interested now to talk about not the quantity but the quality of energy.